You know, buried inside every complex equation, there are these hidden numbers. They're like secret keys that unlock the whole thing. Today, we're basically going on a mathematical treasure hunt. Find them. So let's get right to it with our first mystery. Okay, so here it is. This equation looks like a beast, right? But I promise you, buried inside are these very specific values for x that make the whole thing equal exactly 0. Our mission, should we choose to accept it, is to find those numbers. Now, these secret numbers, they actually have a name. We call them roots, or sometimes zeros. And honestly, the concept is super simple. A number is a root if you can plug it into the function, and the function just spits out a 0. That's it. That's the entire goal. So, how do we actually find them? Well, for that, we need a toolkit. And our very first tool is the most fundamental of them all: simple factoring. Before we go and tackle that big mystery equation, let's warm up with something a little more manageable. Take this one here. This is a classic quadratic equation, and it's absolutely perfect for our first tool. See, what factoring does is it just breaks the problem down into smaller, bite-sized pieces. By rewriting it as a multiplication problem, we can see that for the whole thing to equal 0, either the first part, x minus 2, has to be 0, or the second part, x minus 3, has to be 0. And that immediately tells us the roots are 2 and 3. Boom, done. So yeah, think of factoring like the classic screwdriver in your mathematical toolbox. It's not fancy, it's not flashy, but for the right job, it's perfect. Clean, precise, and just incredibly useful.
But you know, a screwdriver isn't going to fix everything, right? Sometimes you just need a bit more power. So let's grab our next tool.
And that's really the heart of the issue. Not every equation is as neat and tidy as that last one. Sometimes the pieces just don't click together so easily. So what do you do then?
That's when we bring out the power tool. The quadratic formula is like our trusty electric drill. It doesn't care how messy the equation looks. As long as it's a degree 2 polynomial, you just plug in the numbers a, b, and c, and it will churn out the roots for you. It's a workhorse. It gets the job done every single time.
Okay, so we've got our screwdriver and our power drill. We're feeling pretty good. But is that going to be enough for the big one? Let's go back to our original mystery and find out. Remember this thing? This is a cubic polynomial. It's degree 3. Our screwdriver, factoring, well, good luck trying to eyeball that. And our power tool, the quadratic formula, nope, that's specifically for degree 2. So our manual tools aren't going to cut it here. We're stuck. This means we've got to escalate. It's time to leave the hand tools on the bench, step out of the garage, and bring in the heavy industrial machinery. And in today's world, that heavy machinery is code. For us, it's going to be Python, which, luckily for us, has these incredible libraries that are built for exactly this kind of heavy lifting. So in Python, we have two main ways to tackle this. On the left, you've got NumPy. It gives you a super fast numerical approximation. See the decimal there, 0.5? Now on the right, you've got SymPy. It does symbolic math to find the perfectly precise, exact roots. So instead of 0.5, it gives you the actual fraction, 1/2. This quote just nails it. NumPy gives you a quick, reliable estimate, like a quick measurement on a job site. SymPy, on the other hand, gives you that flawless architectural blueprint. Both are incredibly powerful. You just got to know which one you need for the job. So, we solved our mystery, but that just opens up a new one. What happens when you graph a polynomial and it never actually crosses the x-axis? Where are the roots then? Do they even exist? Just take a look at this equation right here. If you were to pop this into a graphing calculator, you'd see a parabola that's just floating entirely above the x-axis. It never touches. So you'd think, okay, no roots, right? Well, not so fast. The roots are totally there, they're just hiding. To find them, we have to open up this whole other treasure chest that contains the imaginary number I, which is just the square root of -1. These are our hidden complex roots. We call these complex roots. You can think of them as having two parts, a real number part and an imaginary part. This allows them to exist on this hidden, two-dimensional, complex plane instead of just our regular old number line. And the cool part? Our computational tools, like SymPy, they can find these hidden roots just as easily as the regular ones. So there you have it. After all that, we've built this amazing, complete toolkit that can find any root, whether it's simple, whether it's messy, or even if it's hiding out in another dimension. This table basically sums it all up. For your simpler degree 1 or 2 equations, you can often get by with manual methods or use SymPy for a perfect answer. But once you hit degree 3 or higher, NumPy is your best friend for a quick numerical result. But here's the big takeaway. If you need absolute, perfect precision for any degree, SymPy is always the way to go. And that brings us all the way back full circle. Our initial mystery, that big intimidating cubic polynomial from the beginning, it's solved. The hidden numbers, the secret keys that make the whole thing work, are -2, 1/2, and +3. We found them. So why does any of this actually matter? Because finding roots, it's not just some abstract math exercise. In the real world, these numbers are turning points. They're points of equilibrium in physics, they're the break-even points in finance, they define system resonance in engineering. They literally describe how our world works. So the question this leaves us with is, what other critical, hidden turning points are out there just waiting for us to find them?